Hi. Alright, hi, yes. Um, Wait, I think YouTube just told me the stream started. Can you check if it started? I mean, I'm not worried if it is started. Okay, cool. Lamau. Okay. Oh, is there a reason not to?
Yo.
Hey, wait, Sharky, can you um give me edit permission to the Jamboard because I think I lost it.
How'd you lose it?
I don't know. My email is this. I'm sending it to you.
Okay. Today's another stream. Okay. And people... editor sent.
There's no wait. Surely there's no personal information. Okay, maybe there is. Like, this is my name, right? But
Yeah.
also,
It's
can you
fine.
subscribers? Maybe I don't know. I guess I'll put it into a different. Yeah, there we go. That should be fine.
Hmm?
Yeah. I just put it into a new window. Can you hear me in the stream, by the way? Or can you hear us in the stream?
Just wait, my parents are calling me.
Okay, sure. Wait, no, like, but in the stream, I mean. Like, you should deafen yourself here. Oh, really? Okay. Even Sharky? Oh. Wait, how? Wait, I can't even see the stream. What is this? Oh, is it? Did I set up the wrong one? Surely it's not. Oh, it is. Oh, I see. Okay, I'll change that soon. Um. Wow, this is huge. Why is this so big? Cool. This, I guess I will delete this.
Alright. What's happening? Oh, we started?
Yeah, we started.
Okay.
Hang on,
Where are we
I'm
at?
trying to see if people can hear you though. You can start. I'm just gonna keep.
Just wait.
Yeah.
Surely people can hear me.
I don't know. You should check.
I am speaking at the moment. Surely you can hear me. If you can hear me, message in the chat. So can you guys... Nope, can't hear you. You can't hear me? Okay. Alright, let's have a look at... So, okay, so people can hear me and that's all good. So that means you can start the problems then. What are you doing, Tony?
Wait, hang on. People can hear you?
I mean, Hayden just said so.
Oh,
in the
right.
chat.
Oh, that's great. Can people hear me?
So, come on. Okay, I have my parents right here, which is a bit... Okay,
Rip. Oh, goods.
yeah.
Wait, I can't even
Let's,
see the stream. Wait, what?
I'm not
so
on the stream.
confused. Is it this one?
Great, now that my parents are back in the house, I'm gonna turn on push to
Is
talk.
it this one? Oh, it is this one. Okay, got it.
There we go, push to talk. Great, now that my parents are back in the house, I'm gonna turn on push to
Is
talk.
it this one? Oh, it is this one. Okay. Wait, I better pause it, otherwise I'm gonna get feedback, aren't I? Okay. Yeah, if something is wrong, then you should probably ping us, but otherwise we're gonna start.
APMO, do we have the APMO questions?
Yeah, well, I mean, I have them. Oh, did we post them here? No, we didn't. I'll post them. There we go.
There we go.
I'll
now
ping.
I can- Okay, let's start with question 1.
Okay. Geometry. Okay, nice.
Mine or yours?
Sorry?
Who's better at geometry of us two?
No, probably you, to be honest. I don't know.
It's good bashing.
Okay.
Let's try. Okay, so ABC.
Oh wait, do we still have 14 slides? Oh, we do. Doesn't matter, we'll just use them. Okay.
Yeah, I'm fairly sure they use the slides more because the questions are a bit harder, I think. I don't know. That's the rumor, at least, that APM is usually harder than AMO.
Yeah, APMO is considered harder than AMO,
Yeah.
usually, yeah.
I don't know. These are points. These two. I'm on slide 1, by the way. That's the tangent to gamma A to the parallel line. Okay. Damn it.
Wow. This is why I always draw like a tiny diagram on paper before I draw like my good one. Okay, let me just do that now. So we have this circle. Gamma be the circle of ABC.
Oh, you're doing on paper, okay.
Yeah, I'm doing on paper for now. Just a tiny one, so I know what it looks like. The DB point inside BC. The tangent to this at A.
Nope, I can't.
Intersects the parallel line to BA. Through D. Oh, it's not that bad. It intersects like this line here, okay. The segment CE intersects, okay, yes. At F, suppose. Oh, okay. Oh, but it's like a suppose question, so you got to draw it in with them concept click as well. Great. This does not look nice to draw the diagram of. Mate, it's supposed to be parallel to BA.
It is.
Wait. You got.
What?
Oh no.
What?
Can't you undo that? Like, you can undo, right, surely? Doesn't matter. It's just draw. Oh, mate. Okay, I'll undo. That's better. Yeah, there we go. I'll draw this line. Oh, E is too close to F, isn't it?
EFE, that's roughly cyclic.
Right, hang on. I'll draw in this line again. Okay, there we go. I should have drawn a bigger diagram. Okay. Yeah, this is great. So, BDEF is supposed to be cyclic. Yeah, this is not a good diagram. But oh well, let's just go with it. Can we even draw straight lines in here? Oh, nope. That's a rip. Okay. Oof. There we go.
BE.
Okay, so
Why did you draw BE?
BE, because it's a cyclic quad, right? You're supposed to have like all the diagonals.
BDF equals cyclic. Okay.
Yeah. Proof that AC, BF, DE, AC. Oh, right. Oh, right. Wait, what? This is so off in our diagram.
I'm sure I can complex batch this. I'm fairly sure I can.
No, don't. Oh my god, what is this? Oh no, this is such a bad diagram. Should we just like take a snip of GeoGebra?
Nah, make it big. I don't want to cheat.
No, but it's like
Now I know it.
even on paper you would be able to draw a better diagram than this. I'm just gonna snip GeoGebra.
This is how we spend the next 4.5 hours just making.
No, yeah, this is a rip. Yeah. I'm drawing a diagram. On GeoGebra, I mean.
I'm just drawing one.
Tangents here, intersects here, segment here, and now oh wow. Wait. I'm very confused. Suppose B, D, F, E are cyclic. Sixth line.
Interesting. Did you take it off GeoGebra?
Yeah. I'm taking a picture and.
Yeah, I push to talk because otherwise you're gonna be hearing my voice back.
Oh, I see.
You want to send the snippet by any chance? Because I tried. And
Yeah. I'm not finished making it. Hang on, that looks. Okay, this looks good. I'm gonna snip it. I'm gonna go to the next frame and paste it.
I feel like you could probably do radical axis theorem. It feels like it. Because you got like BF is like your radical axis, right? For two of the circles.
Oh right, yeah.
Wait, does that?
True. But that means like AE. Hang on, wait. ADCF has to be cyclic too, right?
Yeah. So I guess that's the proof. That's what you have to prove.
Yeah, okay. That seems reasonable.
Can you post this in GeoGebra things so I can actually...
Yeah. No. I've already posted it. It's on frame 2.
Oh, there we go. ACDF. Wait, ACDE, sorry. Yeah. Let's draw that. And now we have to show...
No. Hang on. I'm redrawing that line. Hang on. All right. Sorry. I'll redraw it. There we go.
Law of lines. Okay, can you dot AC, BF, and DE instead?
Can I? Sorry.
Line. Dot the lines. Make the lines dotted.
All right.
Like the, yeah.
All right. Sure. Yeah.
Fair. This is why I like to have a drawn diagram instead, because then I can just control it right there.
True.
Okay, so this angle equals to this angle, which equals to this angle. Wait, equals, oh, yep. Proven, done, lol.
Okay, wait, that's done?
Yeah.
Okay,
So basically, well, I mean, I've done one direction, right? EAC, because this is two direction thing, right? EAC equals angle ABC, right?
Yes, yes.
By old seg. All right, and that equals to angle EDC by parallel.
Yes.
Therefore, E A DC cyclic.
Oh, yeah. I see it. Yeah. So we're done.
Therefore, if the AEBD, if the other one, whichever the other one was, BDFC is cyclic, then my right
BDFE.
theorem is done. And if you go the
Yes.
other way, it's the converse of right theorem, I believe, which is that true?
Wait,
Is
do
it
you...
converse of right? Yes, it is. I remember.
You don't even have to prove the converse. It only says suppose B if D is concyclic,
really?
right?
Okay.
Yeah, you don't even have to
Alright.
prove the converse. So we're just done.
Okay.
Well, that was easy. Yeah, so like...
Well, I didn't think wasting time on the scale die.
yeah. So yeah, we just have like all of these angles are the same, and then this is just cyclic.
And use radical axis to finish off.
Yeah, and radical axis. Cool. Okay, next question. Next frame. What is the next question?
R equals to the largest real number R, which has one condition. If that's in, oh god. A n less than A n plus 2 less than A n squared is R a n plus 1, then eventually it's periodic.
Hang on, I'm loading the
Yes, Brainy.
Wait a minute.
I mean, question 1 of APMO is usually pretty easy. Like, it's usually like about the same level as like AMO Q2 probably. Q2.
Did
Q5.
I get my... Wait.
Actually, some of them are Q2 and Q3, I think. What'd you do?
I think I screwed up the stream. I don't know. Damn it. Okay, I'm gonna remove this. Yeah, I think I was streaming the wrong window for this whole time. That's a rip. Image. 2. Browse.
Okay. The problem in the top right corner is what? Oh, it's
Wow.
what?
No, the comments. Okay.
Oh yeah, my brother decided to walk on the stream, so he's not even good at maths. I don't know why he's doing it.
If a sequence list of positive integers fulfills the inequalities for every positive integer n. Interesting.
The hell is this question? I mean, I see what r equals 2 kind of probably would work, just because
Yeah.
a plus 1 squared.
Yeah.
That's the intuition behind it, but like actually proving it seems. I guess you have to just squeeze it, kind of be like, okay, eventually, show that the gaps between A and N is eventually reducing or something. It's decreasing sequence, and therefore, like, it has to eventually just become, it has to be periodic. Just because this bound just becomes too tight for it to be an integer sequence.
Oh, it's an integer sequence. Lamau.
Well, if it was a real sequence, the harder it gets.
Yeah. No. That's a good point.
I can easily construct a real sequence that works for this. Harmonic works.
Yeah. Okay. Well, I guess we try small cases. So.
I mean, how do you even try small cases?
Like you just start with random positive integers.
Wait. Okay, you want to try my idea of showing that the differences are decreasing eventually between consecutive terms?
Sure. I mean, I don't have any intuition for this right now because I haven't tried small cases.
Neither do I, actually.
Yeah, this is why we need to try small cases.
If R is greater than 2, can we construct a sequence that just that doesn't like become? Can we do that?
Well, clearly by the problem implies that you can, right? Yeah.
Okay, let's try. Let's try R equals 3.
Okay.
1, 2. So this has to be between the next term has to be between 1 and 2.
And no, wait, what? 1 and
root 7, sorry. So 2.
Yes.
Either
right,
1 or
yes,
2.
yes, 2. Yes.
So this could be either 1 or 2, sorry. Yeah. Tree diagram of we worked last time.
Lamau.
What's the next one going to be between 2 and square
10, right? So it could be 3.
2 and square 2 and 3, yeah. Like between 2 and 3, and this becomes between. This has to be 2, I think.
Yeah, I think if you don't take the largest one, it's suboptimal.
But just to make sure. So this one then it can go either 1 or 2 again, I believe.
And then this one.
This thing will always go to like 1, 2. That's a repeating.
Yeah.
Okay, 1, 2, 2, 3. Okay. And what's the other possible choice for this? It's 2 less than equal to.
It's like 2 or something, right? Or you can. It's 2. Yeah. So this one goes from 4 to 10. No, hang on. Oh no, it's like 4 to okay. Let's just make this 13 again. Oh, okay. Can't you just have like 1, 1, 2, 2, 3, 3, 4, 4, and so on?
Can you?
Seems like you can.
I feel like it might stop after a while.
No, because like let's say you have like 10 and 10, right? Like eventually you just have like 10, 10. Then the next one is greater than
10 plus 1 squared. Yeah,
exactly. Exactly.
The thing I said before. Yep, okay. Sure. So this thing, therefore, is a sequence that doesn't work. But can we characterize all such sequences for like an R? Can we construct a rule?
Well, like if R is greater than 2, then I'm pretty sure this kind of thing works, right? You just take A1 big enough.
Yeah.
Like A1 is like R minus like 1 over R minus 2. I don't know, something like that. Surely it works, right?
Yeah.
Um,
Can we just try something? Okay, let's just do some quick analysis on this. So let's suppose r equals to like 2 plus epsilon. Yeah. Then an plus 2 is less than or equal to square root of an squared plus what is this? 2 plus epsilon a of n plus 1. Yeah. Now wait, does this sequence start 1-1, can't it?
Can it? 1, 2, you get...
Yeah, it can.
Oh.
So, yeah, okay.
But, like, if you get...
So what if we just start every sequence with 1?
Wait. Does
like for like something greater than 2, right?
Wait, how?
So
wait, no. It doesn't work. It doesn't. Wait, how does it work? You get 1 squared plus like
3 times 1.
No, what? It's 2 plus epsilon.
No, for the r equals 3 in this case. Sorry. Okay, but here maybe we can just do something similar. Like with 3, you get 1, but maybe like if we set them both equal, because that's like simple, right?
Yes, yeah.
But A1 and A2 to be equal or something. I don't know.
Oh yeah. Right. So yeah, like I was thinking like A1 equals A2 equals like 1 over epsilon or something like that.
Yeah. I don't know.
So if you let
if an is like greater than, that doesn't work. I think.
So for example, if it's like 2.1.
Surely some sequence like this works, right? Just add a constant term large enough, and that should work by your own thing before, right?
Like you mean like if it's 2 plus epsilon, then you just start with A1 and equals A2 equals big
like,
enough, right?
You do this thing, right? Basically this thing, with 1, 1, 2, 2, 3, 3, etc.
Yeah.
But you add some massive term to this, like some massive constant, so that it's
right. Oh yeah. That's what I'm saying. Yeah. That's the same. Yeah. So it will just work. Yeah.
So you just need to figure out how to quantify that. Okay, so let's say A1 equals A2 equals like K, and then we want A3 to be equal to K plus 1 or something, and for some 2 plus epsilon. So K plus 1 less than or equal to square root of K squared plus 2 plus epsilon K, which implies 1 less than or equal to K epsilon, K greater than 1 epsilon. Yep, that looks right.
Okay, cool. So, wait, it is actually just 1 over epsilon?
Yeah.
Wow, nice. Okay, that just means we have to prove that if it's... So now we just have to prove if R is 2 or less, then it doesn't work, right?
Okay, so we'll just...
Like, go to a new frame, I guess, or do we want to...
I just want to put a summary.
Oh, yeah, sure.
If K equals 1 over epsilon and A1 equals A2 equals K, then non-periodic.
Yes.
Where epsilon equals to R minus 2. There we go. Now it's good. Now we have to show the other bit. This seems the hard bit.
This seems like the annoying bit. Yeah. Cool. So So let's just take r equals 2, because I'm pretty sure the other cases just follow, right? If I was less than 2, then clearly, you know.
Yeah.
So now we just have
Yeah, r
an less than or equal to an plus 2.
Am square root of am squared plus 2am.
An squared plus 2an.
Plus 1.
Which we note is less than. Oh, right, yeah.
Okay, so... Okay, I think we need to try some more sequences here. Let's try with 1, 1. Well, we don't know it's less than 8, do we? Because we haven't got bound in am plus 1.
Oh, wait. Oh, right, wait. Hang on. Oh, yeah, never mind.
Yeah. That bound's true, but like we don't have a bound in am plus 1, so therefore we can't actually.
No, yeah, I got. Yeah.
Then we want. Yes, 1, 1's bad. 2. That gets you. 1 or 2, I guess. 1, 2. This one gets you 2, I think. 2, that's the, yep, that's 2, and this one gets me 1, 2, 2. What's this one? 1 less than equal 2 less than equal to 1 less than equal to.
So this has to be like 1 or 2, right, as well?
That's 2. No, it's 2 only, right? Oh wait, yeah, it's 1.
Oh wait, can it be 1?
It's because the previous time.
Yeah, so it has to be 2. And now it's just like sticks at 2 forever.
Okay.
What if we start at like 10, right? Oh, I guess like the annoying thing is like what happens if a2 is like some weird number?
Okay, that's what I was thinking.
Yeah.
K, and then 1, then K, and then what happens? Let's say this is M. Let me know 1 less than equal to 1 less than equal to M less than equal to square root of M. Oh wait, no, sorry, K squared. 2K plus 1, I believe. Yeah. Okay, so let's M1. A3, A4, let's go, how is A4? K or less than equal to A4, less than equal to, square root of K squared plus 2K plus 1. K squared plus 2 root 2K plus 1. Oh, so close to be.
Nested.
Yeah, that's like assuming that A3 that it's up maximal bound.
Yeah.
Just write that in case so. I mean, I'm fairly sure this is like less than, or this is less than K plus 1 square, K plus 1. Like for large enough K, it's gonna be less than K plus 1, right? Just because the square root's gonna be dwarfed by a linear term.
Let me see. So this becomes K squared plus 2K. Oh, right, yeah.
Yeah, that makes sense.
Yes, that's true.
Which means that therefore A4 equals K.
Right, yeah, true.
And just for K large enough.
Isn't this true for like practically all? Wait.
Yeah.
What is the thing inside?
Huh?
What is the thing inside here?
2 root 2k plus 1.
Right, okay. So then that just has to be like, if we just do like if we square both sides, we get like k squared plus 2
Are you
roots.
using
Sorry?
Wait, why are you squaring?
Like, wait, I'm trying
Trying
to
to figure
figure
out
out like what exactly, like specifically it is.
Yeah. K squared plus 2k plus 1. So like, so you can cancel, square again. 4 2k plus 1. Less than 4k squared plus 4k plus 1. So therefore, 4k squared minus 8k minus 3 is greater than 0. Oh, is greater than 0. Therefore, this factorizes to 2k minus 1, 2k minus 3.
Wow.
Oh, wait,
Nice.
no, never mind. I can't.
Oh wait, yeah, it's like minus. That's a rip.
It's gonna be root 7 instead. Wait, it's like 2k minus 2 squared minus 7. Right. So just choose like k like bigger than 3.
Right. So that means the inequality holds whenever k is bigger than 3.
Bigger than 3. That's starting with 1 though.
Right. Oh, true. Yeah.
But I think you can scale everything probably.
Yeah,
Like,
yeah. You can. Yeah.
Oh wait, no, you can't. It's not homogeneous. Never mind.
Huh? What? Where?
It's not homogeneous this term. It's not homogeneous. You can't scale.
No, but like you get like two. Oh wait, hang on.
Fairly sure it's not homogeneous, so you can't scale. So you have to. Oh. Okay, well, that's interesting.
I'm gonna do another small case, starting with 10. This thing here.
I'm just gonna try this. Okay. It's like God. Okay. 1. Let's replace 1. 3, 2, 3, 2 goes to 2 squared plus 4. So I'm just gonna analyze the sequence real quick.
Oh, I think I have I think I got something, which is that yeah. So okay. If so let's say an is not equal to an plus 1, right?
Yeah.
Then in that case, either the odd terms or the even terms cannot increase.
Alright, so you're saying, well, let me write it here. So you're saying an, wait, an less than, so you're saying an less than an plus 1, less than an plus 2 or something?
So like,
This is
I'm saying like, if you start your sequence with 10, 20, right? Then
Yeah.
you can't go bigger than 20.
So so that's what,
every
that's
second
what I'm saying.
term will just be 20. Yeah.
Yeah, so
Or
you're
like
saying
smaller
that's
than 20.
basically what's gonna happen?
Sorry?
This is impossible. You're saying this is impossible, basically.
What is impossible? I can't see what you're drawing.
Frame 5.
Oh, page 5?
Yeah. Is this what you're saying is impossible?
Uh,
If this happens, then this bit is impossible.
Maybe I think so.
Because you're saying it can't be increasing, right?
Um,
Because this is like what?
yes, I think so.
Because you're saying odd and even, so I was like, okay, so just difference by 2, right?
Yeah, yeah.
Let me finish this off screen or please break the screen or should be.
So I guess what I'm trying to say is that,
Yep. So I think I got the same. I got something similar for B large.
how do you write so well with the mouse? This is impossible.
Experience.
I'm gonna use my finger.
Just get good.
Okay, this is what I'm saying. Wait, so after we get this, then it's like... Then it should be pretty easy, right? Because then, like, the bottom, you can't decrease as you go along, which means that, like, the range is now bounded. And that means it will eventually become periodic.
I mean,
With
I'm getting
period
something
two.
similar here, right? If once like you get your term, the difference between the two terms large enough, right? So it's like is equals to a plus a half. If once your b term is basically above your a term, you're dead.
Yeah, that's what I'm saying.
Yeah. So therefore, they have to be equal, which then makes the thing in periodic sequence size 1.
Yes, exactly.
Eventually. All right.
Okay, well, we can write the proof up later. I think that's done, right?
I think we've got the intuition for it at least. And
Yeah. The rest is just pretty much algebra, I think.
Yeah.
Cool, okay. Problem 3?
Yep. Determine all positive integers k for which there exists positive integer m and set of distinct positive integers such that for any integer n greater than m can be written as some distinct elements of s in exactly k ways. What?
Hang on, I'm still configuring
String. Alright.
the stream, yes. Cool, okay. Stream has been configured.
Okay. Question looks weird.
Determine all positive integers k for which exists a positive integer m and a set of positive integers such that for any... Okay. And a set s of positive integers such that any integer...
Or you actually could just be like binary digits, right?
Can we read some? Ah, interesting. Yeah. I kind of get the question now.
Alright, so k equals 1 that binary digits works, right?
Yep. What about k equals 2?
Well, I was
Okay.
thinking something binary digits, but that just adds infinite, I think.
Yeah.
If you have an extra 1 in there, then the 2 1s can replace the 2. But then 2 and 2 1s can replace the 4, and so forth. So you have like infinitely many replacements.
But you can't have 2 1s, right? Because it's a set.
Oh, right. Yep. Can't you be a list? And then array.
Yeah, an array. A dictionary.
Data structure.
Okay, I guess, yeah, it seems to get pretty complicated as soon as you get k greater than 1.
Yeah, maybe that's the main part of the question.
Yeah! So I don't know, maybe there's just no other k, like, or maybe there's, but, yeah.
Wait, no, I've done a question like this before. It's like, crap, I swear I've done a question like this before. It's like, you could write every positive integer as a sum of terms in two sets, right? Such that was one element from each term, from each set, sorry. And I think you can kind of transfer that. Wait, can you? I don't know. Wait, if you replaced a 1 and a 2, right?
Yeah.
With a 3,
Yeah?
you can't do any more, can you?
You can't
Because you
do,
can do 1 and 3,
you can't do anything 2 mod 4.
but you can do like, what if you do like 1, 2, 3, 4?
Yeah, but then
Okay.
everything odd has like 2 ways, and then everything that's 2 mod 4 only has 1 way.
This way, I'm just thinking. So 1 has
Ooh,
one
no,
way.
actually, maybe not.
2 has
That is a
2
good
ways.
point.
3 has 2 ways.
Yeah.
4 has
2 ways?
wait, sorry, my bad. There's 1 way.
Yeah.
3 has 2 ways. 4 has
2.
2 ways.
Yes.
5 has 2 ways. 6 has 1 way, right?
No, it has 2. It has 1, 2, 3, and 2, 4. Because every time you use a 4, you can.
Yeah. 7 has 2 ways. Okay.
Yeah.
So that's it. I think this is probably a Kegel shift construction to improve it.
Yeah, I think so. This might work.
I think you can use binary, right?
Sorry?
You can use binary. And just look at mod 4, right?
Yes. Well, that's what
I
I've been
think
doing. That's what I've been doing. Yeah.
Yeah. So that probably works.
Because okay, so hang on. So everything that's 0 mod 4, then you can like do the normal binary, but then you can replace 4 with 1 and 3. So that's 2 ways, right? Everything that's 1 mod 4 is like.
Well, I mean, if it ends in 1 1 or 0 0, right? You can use 1 3, right? Then you can use the 3 basically. If it ends in 1 1, you can use the 3 2 1. If it doesn't end in if it ends in 0 0, then you can use the 3 and the 1. Wait, 3 and 1. Yeah.
Right. Yeah.
It's really a binary.
Okay. Yeah. So if you consider the binary, this set allows you to construct anything. Yeah. So if you have some binary representation, like 1 0 0 ... and you like drop the last 3 numbers, I think.
Last 2 in this case, I think.
Isn't it? Wait, last 2. Is it last 2? No, I think you need. Wait.
Last 2. Yeah. Okay, never mind. Yeah.
I think it is last 3. Surely, yeah.
This is carrying. That's carrying.
Right. So this set, this set here allows you to construct any binary sequence where you cut off the last three digits on the right.
Yeah.
And then for the last 3 digits on the right, there are like 2 ways to construct each one.
That's what I was trying to...
Yeah. For like large enough.
Yeah. Okay. So end in 000. You can either have it end in nothing, or you can have...
Yeah, or you can have 1, 3, 4.
1, 1, 3, 4. And you know those aren't in there because otherwise you'd see them. For 001, it can either be 1 at the end, or it can be 3 plus 2 plus 4.
Yes.
If it's this, you have 2, or 3 plus... 1 plus... Okay, 1 plus 2 plus 3 plus... Wait, yeah, okay. So this is 1 plus 3 plus 4. This is 2 plus 3 plus 4. And this is 1 plus 2 plus 3 plus 4. Wait, but this one has an extra carry. Does it?
Wait, what is this?
I think. Oh yeah, because then you know this is 1. Okay, you assume that it ends in 1 0. You assume that it starts like this because you know that you're looking at the last 2 digits.
Yeah, sure.
I think.
Wait, I mean, like, you don't really need to. It doesn't matter, right? Because if it carries, it doesn't matter. Yeah. Like, it doesn't matter if it carries.
Okay, good. You just have to show when the representation out the 3-1 with it.
Um, 1 plus 4. 2 plus 3. There we go.
Okay. So that's k equals 2 solved. Now k equals 3. Does 1, 2, 3, 4, 5 work? Look, I tried 3 and it worked, so maybe 1, 2, 3, 4, 5 works next.
Maybe. I don't know, I'm doubtful though. I think the construction... What about a 6? Maybe it's 6 that works.
Maybe, because it's like a multiple of 3, and 3 seems to be nice, because you got that 1 plus 2.
Well, no, I was thinking that, like, each time, like, for k equals something, you, like, add in the next middle number between the powers of 2. So, like, previously you added in the number between 2 and 4.
So is it just doubling 3?
Oh, that's true. Yeah, that's true.
Let's try this. Let's... Yeah, I don't know which k value this would be, but like, let's find out. So 1, 1, 2, 1, 3, 2, 4, 2, 5, 2, 6.
We can probably not... We probably don't need to try the small numbers.
2.
Because...
Yeah, but we need to get the smallest number which works, right?
Oh, right, true. Yeah.
So 1, 2, 3, 2, 4. That's 2, I think. Oh wait, no, 3, 6 as well by itself. 7. 1, 2, 3. Wait. There's like 1, 6. 3, 4. Who's anonymous problem? Why they joined? Oh wait,
there are heaps of people. Yeah.
Yeah, I just realized. 1, 2, 4. Is there any other way of doing these? 1, 2, 3, 1,
Yeah, I
2,
don't think
4,
so.
1, 6, 1, 2. Yep, okay. There's 3, so this is probably k equals 3 or something. 8. So it's like
There's
1.
8, 1, 3, 4, and 2, 6.
1, 3, 4, 2, 6. Anything else?
8, 8, yes.
3.
Yeah.
I think it's k equals 3. What, so every integer works?
Every integer you can get 3. I feel like it.
That would be pretty cool. If every integer works for this question, as in k equals like, all integers works.
Yeah, that would be cool.
But then that wouldn't be APMO. Be like, lol. You missed k equals 12, which doesn't work.
Yeah. That's such a mood.
Yeah. 1, 2, 6, 1. 1, 2.
2, 3, 4.
Yeah, I'm just iterating through all of them.
Right.
2, 3, 4. 3, 6. 4.
Oh wait, why are there 4? That's sad.
What is this? And before it just goes to infinity, it's just like, what? Then we have to go back to the drawing board. See, this is why you try small cases, because it's like...
This is highly sad.
Yeah. Okay, let's try 10. 1, 2, 3, 4.
I've gotten 4 for this too.
Okay.
Maybe, I don't know, maybe only powers of 2 work? That's another possibility, I guess.
What, so the construction is powers of 2 and the thing is also powers of 2?
Yeah, I don't know, maybe. Because for
What?
10, I've already found 4. I don't know if I can find a 5th one, but I don't think so.
Okay. I mean, you just iterate through all of them, right? It's not that many cases. 1, 2, 3, 4, 2, 1, 3, 1, 2, 6, 1, 4. Nope. Okay. So 2, 3, nothing. 2, 4, 2, 8. Okay.
And there's 4, 6 as well.
4, 6.
Yeah.
Yep.
And I think that's all of them.
That looks right. Yeah, past all of them. Yep. Okay. I swear this is 5. Well, I mean, it's been going up by 1 every 3 numbers, so...
I don't think that's a
This is
pattern.
a-
It's gonna like it's got a cap somewhere because the rest of the thing is binary, right?
Yeah.
So like essentially it's got to be periodic,
It
but
would be 4, right? For large enough, it would be 4, because you have 2 choices, 2 ways of making with 3, and 2 ways of making with 6, right? So 2 times 2, 4.
you have 3 ways of making 6.
No, as in, like, sorry, you have 1 way without, as in, like, you have 1 construction without 3 and 6. You have 1 with 3 only, 1 with 6 only, and 1 with both 3 and 6.
Oh, genius! Does that work?
I think so. You just look at the binary. And then I think that generalizes.
Okay, wait. Let's just look at the binary here. What is 3? It's just 1 1, right? And then 6 is just 1
0.
1 1 0. No, hang on.
Covered.
Yeah, it is 1 1 0. Sorry.
Yeah.
1. Ah, great. 1 1 0. There we go. Hmm.
Okay, I need a new frame. I'm going to see if we can work on the general construction. So what's the general construction of these? k equals 2 to the power of like t probably, and we have the construction is like 1 2 dot 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 by 1 2 4 8 dot, and then we union it with 3 6 dot dot dot. What is it like?
Are you on the next
3
slide?
Yeah.
Okay, yeah. You should tell me because I'm controlling the slides.
All right.
I'm controlling the
Yes.
stream.
I'm fairly sure this is our construction for.
Yes. But with this construction, you also have to prove that like k not equals 2 to the t doesn't work.
Oh no.
Yeah, that's gonna be like
No.
more work. That's a rip.
Can we just prove this and then go? That's hard.
Well, okay, let's see. So, I think you're supposed to do something like,
Let's just prove this first, though.
because S allows you to get everything once.
See what would be. What's the minimum number for which it works?
Yeah, I don't know.
What was the minimum number for
Oh, I know. It's the sum of all of the terms in the sum of all of the stuff in the second set.
which?
Because that works empirically too, right?
Yeah.
Yeah, I think so. Yeah, because it was 9, and then for k equals 1, it was. K equals
It's
2.
all numbers in here. They add up to some number. It's like It's either going to be. Wait. No. If you take the sum, you're gonna have something ending 0 zeros and then just like a 1 and there's another bunch of zeros or something.
Yes.
Yeah. It'll be like 1 0 0 dot 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 0 1 0 0 dot dot dot. That's any number in this is basically written as this. And since there's like 2 ways of writing this, yeah, okay. So I think we can prove that fairly easily now. It's just binary stuff. Now let's show k not power of 2 doesn't work. Okay, why doesn't k equals?
Yeah. Or maybe we just haven't found a appropriate construction. Who knows?
1 2 3 4 5. I'm telling you, man.
Well, you can try it, but I don't think it will work. It just doesn't feel like it. My gut is telling me it doesn't work.
Damn, my kind rejects the combi noodle. Chinese noodle soup. Combi noodle soup. Okay. This thing's that combi in number theory.
Sorry?
This is the number theory.
What?
This is combi number theory.
Oh, right. Kind of. It's more combi, I think.
Yeah. Therefore, you should solve it.
Wow. Yeah.
No, I did not solve anything on paper.
I don't know. I don't think k equals 3 works. I'm trying to prove why it doesn't work, right?
What do you mean?
There's 3 now. For 5.
Yep. And 6 has 3, I think.
Yes.
1 2 3 2 4 1 5. 3425 124. H, so that's like 1.
H has 4. Rip.
God damn it.
Wait, does it have 4? 1, 2, 3. I think I. Oh, no. Yeah, it does have 4. It does have 4.
Yep, I say 4. Hmm.
Um.
Surely the construction's worth like 5 marks, right?
I don't know. How hard is the rest of the problem, though?
Hmm.
Three.
This feels hard.
Yeah.
Should we move to the next question? Because I have no idea how you're supposed to improve that a K doesn't work.
I mean, I'm trying to say like suppose every number greater than like 100 has exactly 3 ways. Oh wait. Yeah. What about recursion?
Not sure.
So like the only barrier to recursion is like you can't repeat a number that you've already used, right? Because otherwise it's literally just a recursive formula.
Mm-hmm.
Um, let's see. So hmm. Three. So if there are 3 ways of making each number, then for any number that you can make, okay, wait, hang on. So let's say, like, let's assume that you can make. Let's assume this works for k equals 3, right? Like, then if you can make, say, 30
Yeah.
in 3 ways, if we did like the recursion thing, then it would be like the number of ways you can make 14 plus the number of ways you can make 22 plus the number of ways you can make 25 and so on, except that like for each of these some of them may already use like the numbers.
Well, okay. So what happens if like the gaps between your sets like too big? Like it equals to like A1, A2. Then like there has to be bound on the side on the gaps between, right? Because otherwise you just get like infinite. You just don't get enough representations.
Yes, the bound is like a n has to be less than 2 to the less than or equal to 2 to the n.
It would be an infinite set. It has to be infinite. Okay. I mean, we know k greater than equal to 3 now, right? We just have to look at k greater than equal to 3. So there has to be, every number has to have at least 3 representations.
Yes.
Okay. A1 plus A2. That means that this has to be like bigger than, for this has to be true for some I large enough, right? Otherwise you just get this has 2 representations. At most 2 representations, right?
Yes.
That's this is like a binary thing, I think. Yes, so that's a property of this. For I large enough, that has to be true. How is that useful? What?
Look at the chat, Livesolve chat, the bingo. Oh my god. Lamau, Tony says Lamau 3 times in 15 seconds. Lamau.
Yeah, you did. You just did it 3 times. There you go.
Yay, there we go.
Okay. Okay, I have an idea. I think for like, based on this construction, I think we can. I have a hypothesis that like, if x in S, x large enough, then the next biggest element in X and S has to be 2x.
Oh, okay, right.
Yeah. Because then you get you can get that extra representations, right?
Right, yes.
I don't know. And this might not be true though. Because this seems too good to be true. But like, if this was true, that's pretty nice.
Um. Hmm.
I mean, like it's true with that constructions, right?
Yes. Yes.
This is kind of based off this thing where, hmm, how though? Sure, you can show the end like it's at least 2x, right? I'm just gonna new.
Oh. Let's see.
Like x equals to like 100m, I think works probably. Just make using Ross's technique. A Google is basically large enough,
Right, are you on the
right?
next slide? Oh, you are.
Yeah. So suppose x equals to this, and in wait, x is like the smallest element is right.
Yeah.
And this is in this. Okay, so this is sufficiently large. A Google. I'm fairly sure this should be enough. And then, if a less than 2x, we should somehow get a contradiction. Uh, okay, so we know that there exists, if like, there exists m ways of writing a. Wait, no. Does this work? No, it doesn't work. I don't know. Never mind.
Okay, maybe another idea. We can look at the binary representation again, right? Because the nice thing about the binary representation is like, um, since you can only use each element in the set once, like a binary representation is like the natural way to represent which elements in the set that you're taking in the sum.
But I feel like the binary representation might be restricting us, kinda, because we might get focused on one too much. Because you have to be work for every single sequence, right? Not just something that's based off binary.
Yes, but um, if you take a non-power of two and put it in the set, then if you represent that in binary, then I don't know. Like surely that can help us in some way. I don't know. um, uh, waiting.
Let me just get rid of this restriction because I got what? Hmm. Listen up this movie.
你们小声一点可以不？
Hmm.
你们小声一点可以吗？我在，对啊，我在跟你们说话，对啊。哎呦，妈妈！啊？你在干什么呀？Sorry, I'm back. I had to leave for a bit. Wait, did you just clear that?
Yes, I couldn't. I thought it didn't work. So
Oh, right, right.
it.
Okay, so yeah, I'm trying to think of a representation that like easily shows that our power of two representation works, because I think that will help us prove that like nothing else works.
Maybe show that like if an odd prime divides the number k, then like, it doesn't work. Maybe something like that.
Right? Yeah. Maybe.
Because like with the primes, you know that you can't, because they're not factorable. But like you can't break them down in small pieces. That means like the number of ways of splitting using the counting thing has to be like p, like the prime itself. It doesn't seem like it should work.
Oh right. Yeah. Maybe. Yeah. Okay. Maybe you can show that. Um. Okay. Does the power of two? Do all powers of twos have to be in S?
I don't know, but it's certainly useful when they're in this.
Yes. Right. But like, so firstly, you have to
That
have
goes back
one and two.
That goes back to my hypothesis of whether if x is in there, then 2x should be in there.
Yeah. 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 Okay. Wait. So if we prove this, then that also proves your hypothesis.
Yeah. Okay, sure. You can show that the next smallest number has to be at least 2x, right?
Sorry.
Or we can show if x is in there, at least the next smallest number has to be at least 2x, not definitely 2x, but at least 2x. Because otherwise, you get too many ways of doing it, right?
Wait, but like you can have 1, 2, 3 in the set, right?
For large enough x.
Oh, right, right.
Because otherwise, you just get too many ways of doing it.
Maybe, yeah.
That's why I was doing the Google thing with it before. But I'm just thinking how you do it.
Um. Hmm. Hang on, sorry, I'll be back.
Right.
Okay, sorry. 你们小声一点可以不？哎呀！ 你知道别人听得见你的好不？ Okay, can you... Is it possible for 4 to not be in this set? What happens if 4 is not in S? So clearly you have to have 1, 2, 3.
Wait, I just looking at the cases we have for k equals 2, right?
Yes?
Every possible sum of a number contains every single element less than it.
Sorry, say that again?
Okay, so every single way of having the numbers add up to the target number
Yes?
contains every single element.
Oh.
Don't know if that's useful, but it's weird. Like, look at 8, for example. It has 1, 2, 3, 4, 6, 8. Exactly once. For me, this holds true. Because that's just pretty funky if it is.
Oh, I see what you mean.
Yeah.
Well, it's not true for k equals 1, but you know.
True for every single one less than equal to.
Sorry?
It's true for every single element less than or equal to. Like, every single element less than equal to 8, right?
Yes?
It will be included in the sum for 8.
It will be included in some way. Well, it doesn't work for k equals 1, right? Because then you only have 8 as the representation for 8.
Oh, right, yeah, okay. So for k, at least k has to be at least 2, I think.
Right, okay.
Yeah. I think. Because I think you can just use induction, right? Well, wait, no. You can use induction only on the terms that are in the set itself, I think. Yeah. Let me just try this. So like 4. Wait, never mind. 4 doesn't work for it. Hmm.
1, 2, 3.
I don't know. Oh, look back on slide 18.
Sorry?
Look back at slide 18.
18.
8, sorry.
Right, yes.
Just contradiction. I'm trying to bound the next largest element. I just had an idea for it, and if this
Right.
is true, then there exists m ways, and without using y. But since y also works, therefore there's m plus 1 ways, and that's a contradiction. Therefore, either x is less than equal to 3x, y is less than 3x on 2, less than 3x on 2, or y greater than equal to 2x. I mean, I dealt with like, what is it, like half the cases. And the top is true just because, like, you know that the elements have to add up to at least x.
Oh. Wait, so is y supposed to be the next greatest element
Yeah.
after x?
Yeah, next to the greatest element after x. Yeah. Okay. Let's have a look at 2x.
Are we assuming k is at least 2?
K is going to go to. This should be. Why am I doing m? Wait, no. K is like at least 2. Yes, as at least 3.
Okay, yeah, we can assume it's at least 3.
And m is like the smallest number that was. Whatever. Wait, did I mess up my variable? Please don't tell me I messed up my variables. Let me think about this again. I think I messed up my variables. I did. This should be K.
Okay.
Now, it doesn't really matter because M isn't important.
Oh, I have another idea. Well, I have a new idea. So, being able to write each number, the same number of times for large enough n. Yeah, so like given the condition in the problem, we only need to find a finite set of numbers that sum to all the remainders modulo modulo a for some a, and they have to sum to all the remainders modulo a like the same number of times, and then after that you just do like you add a and then you add 2 times a and then you add 4 times a and you add 8 times a and so on.
Okay. It seems hard. But if you have the idea, see if it works.
Yeah, okay.
Because I'm kind of confused on that. How many ways are there writing 2x using this?
Oh, hang on, hang on. Okay, this is really promising. Okay, okay. I'm gonna explain this idea to you. Okay, so go back to slide 6 when you're done writing, whatever you are.
I just had a breakthrough myself.
No, okay.
I think I proved the hypothesis,
Oh, okay.
which is also pretty good, I think. Because basically, 2x has a way of being if you consider 2x,
Yes.
you can write it. There's a way of having it add up without using x because k is greater than 1.
Yes, yes.
Again, like x will be in one of them, but x won't be in both of them. So therefore, but then since there's a 3x on 2 thing as well, that means you have like m plus 1 ways again. Like m plus 1 ways if 3x on 2 is in the set.
Okay.
Which is a contradiction because we only have m ways.
Right, yes, yes.
Wait, sorry, if y, y less than 3x on 2, sorry. Which is a contradiction, which means that therefore y is greater than 2x.
Right.
Which means we get that doubling thing. Well, we get kind of the doubling thing. We still haven't proven that
Well,
equals 2x.
what I proved is that supposing the doubling thing is true, the only possible k are like powers of 2.
That's great. So you just need to prove now.
Yeah, yeah, exactly.
We're working in different directions.
Lamau, yeah.
Okay, that's good. Then you just have to show that it's less than or equal. So you just show the 2x, right? RTP, 2x in this. That's literally all we have to prove.
Wait, where are you? Oh, you're on page 9, okay.
Yeah. That's a way too big box. This question's so hard. What the hell? So if 2x isn't an s, then we just have to if 2x is not an s, then just show there's m minus 1 ways of writing it. The number of ways of writing 2x. 2x is m minus 1.
哎呦，妈妈。
So, this implies that if x not in the sum, then one way, I think. Hmm.
Um,
This seems hard.
hmm.
I'm thinking like maybe you can like remove a term and then add something else into it. I know it's like bad, but it's
I don't
gonna
know.
be nice.
I'm thinking about other stuff now, like other. Uh, I'm thinking about some like density arguments, but yeah.
God,
Okay. I think I also proved that if you do have a doubling thing, then you have to have powers of two.
nice. Is this a contradiction? Yeah. Well, I mean, I think this works. This contradiction. Or and I'm fairly. This is just absurd case for x big. Okay. Therefore, flex in this. Yay! Got it. Have a look. It's kind of. I think it works, but it's a bit weird.
Okay.
Slide 9. So have a look.
Yeah. Okay, so if 2x is not an s, then we need to prove that the number of ways of writing 2x is m minus 1.
Yep. So if like x isn't in if x isn't in the sum, then there's only one way of writing it. Yeah, that's what you have to show. Essentially.
Oh, wait, because there's m minus 1 ways of writing x.
Yeah.
And so if you don't use x,
Then there has to be one way.
right. Yes. Okay.
Yeah. So then you consider this sum, right? The specific sum that doesn't contain x, and you look at the elements in that sum.
Yes.
If those elements are too small, then you can actually remove them, right? Because if you ignore that, and then you consider the numbers between x plus m, sorry, k, my bad, it should be k. Yeah, sorry about that. So if it's between, if you have elements that are like less than x minus k, right?
Okay.
Then you can consider what happens if you remove them, and it's like the numbers between x plus k and 2x. There's k ways of writing it without that term, because you can ignore it, and then it should still work because of the k thing. Like it's kind of inductive, I guess.
Wait. What?
It's k plus 1 ways with the x minus k. It's weird. I'm not entirely sure if the argument works, but I feel like it works. Might not be being clear though. Remove z. Remove z from s. And like, if you include x in the s again, right? Then there should be k ways of doing it. Yeah, k ways of writing a t.
Wait. What does x minus k have to do with?
It's like a bound, right? Because if you have it too far, if you like, you want to have it so that you can get the k ways of writing it. So you choose like, you basically look at the terms that are far away from.
Suppose there's such that z in the sum, not
Maybe
including
k is
x.
too small.
Okay, remove z from s. Then for all t between x plus k and 2x.
With k ways of having them without z but including x.
Okay.
But then if you include z again into s, then there should be k plus 1 way, because there exists a way with z.
Right.
Yeah.
I'm just gonna trust you.
And then therefore that's impossible, and therefore z is greater than x minus m. X minus k. And that's just absurd, right? If all the sums are greater, if all of them are greater than x minus k, then you just get like contradiction for x big,
Yes, yes.
and therefore 2x is an s.
Okay. Okay, sure.
Yeah.
Wait, but did you prove that 2x is the next largest after x?
Well, it has to be. That's why I've
Right.
tried.
Okay,
I'm looking
okay.
to get the next largest element.
Right, right, right. Okay. So
Um,
you've shown that eventually the terms in S just double.
I think, assuming this isn't like a fake solve.
Right. Well, okay. So if that's true, then I think we're done.
A, but yeah, don't know how legit the argument. Should we just go to the next question? It's basically we'll just assume it's done and
No,
then
wow,
look back
sure.
at it.
Okay.
Let Z denote the set of all integers. Final polynomials P with integer coefficients satisfy this for any infinite sequence in which each integer appears exactly once. Okay, the existing integers I less than j, so that k is just that. What? Where isn't polynomial? Oh, we get tagged. We didn't say the rest is computation. No, we assume that's not a fake solve.
Wow.
Pay attention to the stream. It's not computation. With the computation, it's easy. We're just assuming that we didn't fake solve. Yeah, that's
Okay, next problem.
skip hard question. No, we solved it as well. We're just not entirely sure if it is. Not that either. We have that. That's the first part. It's none of them.
Wait, where are you even talking in?
Live solving.
Live solving? What? I don't see anything in live
Live solving.
solving.
In the live solving. He's okay. So let's look at problem 4. This looks. I can't tell if this is easier or harder than problem 3.
Right.
This looks weird.
Satisfy the formula for any sequence of integers.
I feel like a linear function won't work.
Well, I haven't even read the question yet.
Okay. It looks weird. This looks so weird.
Yeah, what? Okay. This is very
like
weird.
Mine doesn't work. Something tells me P is a line that doesn't work. So surely you can just make the sum like bounce around the line without actually reaching it. Right?
Sorry, wait, what? Say that again?
Make the sequence bounce around the line so it doesn't reach. Oh, I know. So suppose gradient like suppose p of x equals to like ax plus b.
Yes.
Wait, I think it only works if A is even. We don't. Oh no, you sure you can adjust forward? Then you'd be like let's just do this real quick. Then you go like A, A plus one, A minus one, and then you go A plus two, A minus two, right? See, sequence never would lie on this line or something.
Wait. Hang on. The problem says. Wait, are you not wearing headphones?
Huh? I am.
Oh wait, I can hear myself. Like when you're talking, I'm getting
That's
some.
odd.
I'm getting some echo, but I don't know why. Anyway,
Yeah. So anyway, so as I was saying, if you can get, I'm fairly sure this just makes it not work. Should be A plus B. Yeah. And this is like B is like B not equals 0. Oh wait, it's a subset of the sequence. Never mind.
hang on a minute. For the linear case, can't we just take the sequence mod A and
That's
we
what I was
just
doing.
sorry?
Isn't that what I was doing?
Yeah. And then all right, yes. And then yeah, okay, so you need to get to some to B. Okay, yes.
Not just from the start to the end. It's any subsequence.
Yes, a consecutive subsequence, right?
Yeah.
Except like this is how you prove I don't know if you've heard the problem that goes like um prove that I think it goes if you have any set of p integers, then there is a subset such that the sum is divisible by p.
You mean Cauchy Davenport?
I don't have no idea. Is it that?
I think it's Cauchy Davenport.
Anyway, yeah, that's just like the way you prove that is by like considering the consecutive sequences, right?
There's something similar to Cauchy Davenport. I can't remember.
So in the end, what you end up getting is that, um, yeah. Okay, so all linear functions work.
They work? Yeah, I think so. Because it's like, okay, I think there probably exists one that is mod just works.
Yes, and also I think an important idea in the whatever like Cash and Divin, I don't know what you said, but in that theorem is that like um if you take this like if you take the sum of the first one and then the first two and then the first three and so on, then you get a sequence mod p, and that has to be the same mod p twice, right? By pigeonhole principle.
Yeah.
Yes, and then once you get that, you then take the difference of the two
So
sums.
therefore, there's two sequences that have the same residue.
Yes, and
So
yeah,
that
and the difference of the two sequences is
is
also
going to be zero.
no,
It'll be
wait,
zero.
what?
It'll be zero mod p then if they have the
No.
same
Oh
residue.
yeah,
Therefore, yeah.
but like if you just consider the terms of each sequence, right? Then the difference of those two sequences is also a consecutive sequence.
I use that in some programming problems.
Wait, what? No. So like, if you consider, okay, I'll
Yeah,
draw
yeah.
it.
I'm very saying,
Yeah, cool, okay. So that means all linear functions work. So I guess, I don't know, conjecture, quadratic and above doesn't work.
Well, I mean, I was thinking quadratic does work.
Wait, what? Does it?
I thought it would.
Oh, I thought it wouldn't. Okay, maybe it does. Maybe all of them work then. I don't know.
That Wait, never mind that. I might be mistaken myself. Might not be. Oh, I don't know. Okay, let's just try to construct a sequence that doesn't work for every polynomial.
For every polynomial. Oh, right. I thought you meant,
The,
yeah, for all polynomials, but you mean like for each polynomial, right?
yeah, that's the difference.
Yeah. So I don't know. Let's just try px equals x squared. Or is that dumb? Oh no, that's not dumb because I is less than j.
Well, surely just odd. If you add odd numbers and even numbers, then it shouldn't work, right? If you keep adding the odd numbers and subtracting the even numbers, then it'll always be between two perfect squares.
Um.
Something
Wait.
didn't work.
Say that again.
Just wait. Let me think. Two like you start with an even number
Yes.
and you go odd, and then you go even again. Okay, this is what. Let me think about this bit. Like this sequence will never be perfect square, right? Well, can you?
What do you mean? Like 1 is a perfect square, right? Surely.
No, it's I less than j. No, it says I less than j.
I less than j.
At least
Oh, so
300.
it's at least 2.
Yeah.
Okay, I see. Wait, hang on. But if it's at least 2. Okay, no, we're still fine. We're fine. Yeah. Does that even change the question that much?
I feel like it changes it dramatically.
Okay. Maybe, yeah. But in this case, wouldn't you just go like 0 minus 1 plus 2? That's 1, right?
Because think about it. Otherwise, it's an infinite sequence of integers, right? If you didn't have the I less than j condition, then there exist perfect squares in that infinite sequence.
Oh, wait, it can. Wait, oh.
So therefore, it does dramatically
Oh,
change the
because
question.
it's a bijection, right? I keep forgetting. Oh, right, good point. Right. Well, you can construct this sequence. Oh, Okay. You just make it negative, right? Like you make any partial sum negative.
Yeah, but that would imply every time
No, you can do that pretty easily. You just go like, um,
zero.
no, don't start with. Wait.
Like 3. Wait, 3 minus 1. Damn it.
No, why don't you start at some negative number, right? And then you go up, down, up, down, up, down, and so on. You start at some like negative 10, yeah, and then you do like negative 9, negative 11. Yeah, like this. Surely this works. Or maybe it doesn't.
From the start, it's any subsequence, consecutive subsequence.
That's annoying.
Okay, let me just. Suppose you have a sequence, right?
Sorry?
Suppose you have a sequence A1, A2, dot, alright,
Yeah.
and dot, 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 and you consider S1, Si equals sum, I equals
Yeah,
1.
sure, okay.
Wait, I again, SS,
Look how, yeah.
AI, right? Therefore, you just have to look at like Si minus Sj, right?
Yes.
Where Sj minus Si. Where, well, I mean, J is like greater than I. I plus 1. That's be at least 2 times.
Oh, I have another idea. You do the bijection, but you do it like, you put 2 negative numbers, and then you put 1 positive number, and then you put 2 negative numbers and 1 positive number, and so on. Surely that works, right?
Like this.
Yeah, like that. I think that works. That seems like it should work.
Yeah, probably.
So I think... Okay. My conjecture is that for all polynomials of even degree, there does exist such a sequence.
They exist in the easy sequence. Yeah,
Yes, you can construct a sequence, yes.
But it's just odd, that seems hard.
Yes, odders seems a lot harder. Because I think we've already done even, right? You just need like...
That kind of thing happening. Just
Yeah,
be like
yeah.
the lowest. The polynomial has the lowest turning point to it, and you just consider the sequence starting at that value,
Yeah,
and then like down, down, up, down, down, up, down, down, up.
yeah,
down,
pretty
down.
much.
You're using linear cough greater than 0. You can just say, be like,
Yeah, we can log this surely because the leading coefficient could be
I was just
negative.
negated.
Yeah, exactly.
Okay, this should work. That's your sequence that works for it.
Okay, so now
Odd.
odd. Yes.
You did half the question.
So um. So I guess we should. I guess the conjecture is that for odd it doesn't work, right? Like as in, there's no such sequence.
Wait, how do you know cubic doesn't work though?
Well, I don't know. I'm just guessing, right? Because otherwise it's gonna be.
It could be like it would be just like the APMO to be like all odd degree polynomials work.
No, but degree 1 doesn't work.
It does. You just proved it does.
No. I proved that there always exists. There doesn't exist such a sequence, right?
What? I thought you proved it exists.
No. There doesn't exist such a sequence. Isn't that the
Wait.
theorem that we were just talking about?
I thought you said they exist.
So like the result for even polynomials and linear polynomials is opposite.
Prove that. What?
Wait. So for linear polynomials, no sequence has that property, but for even polynomials, there always exists a sequence with that property.
Are you sure you're reading the question correctly?
Am I?
I think you looked at the contrapositive of it.
Oh wait, for any infinite sequence. Oh right. It's
Yeah.
no. I'm reading it correctly. I'm just not saying it correctly. So okay. I'll try again. For any linear polynomial, any infinite sequence satisfies that property.
Okay, good. That's what I thought you said before, when way back.
Yes, and for any even polynomial, there exists an infinite sequence without that property.
Exactly. That's what
Okay.
we just proved.
Okay.
Good. Yeah, so you're just saying the contrapositive of that.
Yeah. Okay. So what I'm saying is that for all odd polynomials, the result is the same as the linear polynomial. That's the conjecture, I guess.
Yeah.
Okay.
Wait, does the constant polynomial fall under the linear polynomial? Because I'm fairly sure constant polynomials don't work.
No, because constant polynomial you'd be like modulo 0, right?
Yeah, so that doesn't work.
So
Because you can just jump up and you can just jump around.
Mm-hmm. I mean, it's the same as the even case because you don't have a minimum.
Yeah.
Sorry, you do have a minimum, so it works.
Yeah.
Yes.
Yeah. Can we inductively construct a sequence?
For odd,
Yeah.
doesn't that contradict the conjecture?
No, construct a sequence that doesn't work, as in that will always avoid the polynomial.
Yeah, that's like opposite of the conjecture, right?
All right. Yeah. I'm just thinking though,
Yeah, I don't know. You can try.
because if we can't, then yeah, that proves the conjecture. And otherwise, well, we get the question anyway. Okay, wait. First, let's just a small case.
X cubed?
You avoid x cubed. I feel like you can. I don't know. So let's just start with 0. Then you add like 2 to it, and then you get like 1. 1 works. You go -1 does not work. -2 does not work. 3 does work. -1 does work.
No, it doesn't, because 1, 3 minus... Oh, hang on. Sorry, it does, yes.
Wait, did 0 to 1 -1 work? No, it didn't, because 1 -1. Okay, so this is fine. Then does -2 follow for the next one? No, because then you got 3. So -3, I believe. 6, 2, yeah, and it's bad. So let's go 4. Basically, I'm just choosing the smallest absolute value, smallest one with absolute value.
Yeah, let's try that, yeah.
And then if like, and then I just favor positive integers in there. 4. Let's try that. 6, 5, 9. 4, 3, 7, 2, 6. Okay. Now -2.
I mean, if we really wanted to make it easy on ourselves, wouldn't we try to use the same thing as the even case, except that like you just have to be slightly more careful when you like, because if you just start at some like arbitrarily large number like 1,000, then you don't have to worry about as many cases, right?
Take 1,000. I don't think it's a good idea to start them with the sequence itself because it might be a bit if it's metric. I don't know.
Because it's like okay, I don't know. Maybe only linear works because I feel like maybe there is also a construction for odd
Yeah. I feel like because
polynomials.
you have the gaps get really big, right, between consecutive integers.
Yeah.
Sure, you can slip and like it doesn't work with linear because of your modular thing. So
Yes.
you can't slip there. Why is this hard?
I don't know. What are some properties of integer polynomials?
The divisibility thing. Gas lemma. This is hard.
Rip. Yeah.
David.
I don't know. This seems kind of messy.
Hmm.
Hmm. Like when you try and come up with a construction to even prove that it, avoids all of those numbers, that's just annoying.
Yeah. Wait, I think my work though.
Sorry.
My you saw how I was constructing it, right? I think that might be all we need to make it work,
You mean like just take the absolute value thing?
and give preference positive integers. I think that might just be like a way of inductively constructing the sequence.
Hmm. So like, you're saying that at no point does a number become impossible for all future.
Yeah.
Like, okay.
So actually, I would start in the sequence itself. Start out of it. So kind of with your thing about starting somewhere not in the sequence, maybe.
Yeah, like start somewhere like just arbitrary so that.
I don't know, like two. Two's like far enough.
Sure, yeah.
Two. Then what's the next number? Zero. Can go there. Then what's the next one? Can one go there? Yep. No. Nor can minus one. Um, at this point, as subsequence is 2 and 0, so we can't add to any of these. 1 minus 1 doesn't work here, minus 2 does not work there, minus 3 works.
-3 doesn't
Okay,
work. 3, yes, 3 does work.
so now 3
One,
subsequence.
one works.
1. Yeah. Because basically just check every sequence ending with that. And then minus 1 doesn't work. Minus 2? No, minus 3.
Nah, -3 doesn't work.
Minus 4 then.
4 doesn't work either.
Minus 4? No.
-4 doesn't work either.
5? Yep, 5. And then now let's start again from -1. Well, what's these? Add like 5, 6, 9, 9, 11. So -1, bad. -2.
That's fine.
Yep. So it's -2, 3, 4, 7, 7, 9.
So -1 doesn't work.
-1.
-3 doesn't work.
I think -1 works. Oh, wait, no, 9. Okay.
No, yeah.
-2, 3, minus 3, nope, -4, nope, -5. Well, 4, does 4 work?
4?
Yeah, no, it doesn't work. No, it doesn't work. 4 plus
Right.
4.
Yes.
Okay. -5.
Nope.
Um,
4 -5.
Yep, okay. Okay, 6 then. That gets us. Yep, looks good.
Right. Well, okay, so firstly, one of the things I noticed is that um, obviously you can always continue the sequence.
Yeah.
Yes. The problem is, can we get every number in the sequence?
Probably it won't be that like some numbers won't pop in, right? For large enough, if when the sequence is large enough, adding small numbers will not dramatically shift the distance from a cube, right?
Yeah, yeah, that's what I'm thinking. Because there are only a finite number of numbers in the thing in the set at a time.
Minus one. No, minus two. Oh, sorry, then minus three.
-3 would work.
Minus
No, no,
three
no,
what?
no, no, it doesn't. Because 4 minus 3.
Oh yeah, okay. Four. Nope. Minus four. Nope. Five.
Nope.
Nope.
-5.
Doing that. Nope.
Nope.
Minus six. Minus
Nope.
seven. Nope.
Se-
Why does the seven work?
does
Seven must work.
7... Doesn't... no, wait. Yeah, 7 works by itself, doesn't it? Yeah. Okay, I don't think we need to do any more, because I don't think it's going to give us that much... I don't think it's going to be that useful.
I just want to see when minus one comes up.
Oh, right, true, okay.
That, like, yeah. Okay, I think minus one just works.
Right, okay.
Because basically I wanted to be sure that yes, every number is beat. And now I think we can inductively prove that this works. Wait. Okay, that's fine. Minus three, I think, fits in here.
Yeah, I think so, yeah. Wait, why are we still doing this?
I'm doing it just to see if it's proper. Then.
Sure.
It's totally not because I'm stuck at the moment, just trying to extend them until I'm happy with, like, yes, we have got the minus 4, minus 5 in there as well. Can you prove this by induction that it will still contain everything, though? There has to exist a number. We know that's definitely easy to prove. Just choose, like, the number large. Like, the issue is you have to get every number in there.
I mean, one way to include... Okay, hang on. This is a promising idea. So add a sequence of... Add like a really large cube. And then add a 1. Like, oh, so okay, wait, no. First, let's suppose that we're missing a 1, right? And we need a 1 to appear. Then what you can do is you just add a really large cube. And then you can add a 1 after that.
Yeah. Are you using Fermat's last theorem?
No. Wait, what? No, I'm not.
Okay, I just thought for a second. Wait, x cubed. Add that on. You don't want that to be perfect cube, so therefore x cubed plus something is not a perfect cube. Like that looks like Fermat's last.
No, because if that cube is large enough, then the distance between cubes is it's just huge,
Exactly.
right? Yes, exactly. Which means that you can just add like a 1 on there. Oh, wait. What if one of the terms is like -1?
So you add a large enough term so that they're all positive, right?
No, as in, what if one of the terms is -1 compared to a cube, right? So like,
Oh, right. Okay.
yeah.
Okay. And double to
No. It's still fine. So you take the range of the sequence of the sums. So in this case, it's 18 to -4, right? And the range of that is 22, and 22 fits in between in between 1,000 and 1,331, which is 10 cubed
Yep.
and 11 cubed. So you just add some number between that, and you like put the entire sequence in between those, right? And then you add the one, and it's definitely guaranteed to work.
So therefore, we can probably do the same for all of them. Just have to formalize it.
Yes, I feel like you can do the same thing for every small number, which means that you can do the same for every number, right?
Yes. Yeah, you should be able to.
I don't know. Doesn't that finish the problem?
That makes it. That seems a bit too easy.
Yeah. Did we fake
Problems
solve?
rigorizing it is probably difficult though.
Sorry?
Maybe rigorizing that might be a bit more difficult than anticipated. Though. I don't know.
Maybe.
Try rigorizing it. I don't know.
The only problem I can see is that, like, if you add some big number, like 1,100, to this sequence, and then you add 1, then suddenly your sequence, the range of your sequence is now really huge. It's like 1,000 and like 130 or something, right?
But, I mean, you can keep going bigger and bigger.
Yeah,
Right?
exactly. So it doesn't matter. You just find difference of two cubes greater than 1,130, right? And you just repeat the process.
So you just like add 1,000, and you're like, okay, fit all the small numbers you can in there. But when they find the first one that doesn't work, add another. Wait, but how are you getting negative numbers in there?
You do the same thing. It doesn't matter. Like if you're missing like -1, you just do the same thing.
Okay, but like you have to make sure you don't have a one at the end, right?
What do you mean?
Oh wait, no, you're adding a big number first. Okay,
Yeah, exactly.
okay,
Yeah.
you're good.
So,
You just keep adding big
but
numbers.
in this case, you don't even need the algorithm anymore, right? You can just add a big number, a small number, and a huge number, and a small number, and like an even bigger number and a small number, and you just keep doing that. That should work, right?
It should.
So, for example, okay, let's say we have some cubic, right? Let's say it's just x cubed. Then let's first add like, so we want to include 0. So we first add something so that it goes between two cubes. So let's add 4, right? Then you can add 0. And then now the range is 4. So we now add some other number so that our range lies entirely between two cubes, and then you add 1 or something. And then your range is now like 5, I think. So, you just you now add another big number so that it lies between two cubes with difference greater than 5, and then you add -1 or something like that.
Yeah.
That should just work, right?
What the hell? It seems like an intuitive idea, roughly.
Yeah,
It?
like it doesn't even what? I'm surprised this works. If this does work, I'm. This question is kind of weird.
Yeah. Easier than P3.
Yeah,
Two years in
wow.
a row.
Should we go to the next problem then?
Sure. Problem
Okay,
5.
okay. Let's just hope we didn't fake solve that.
Okay, let n getting on 3 be a fixed integer. The number 1 is written n times on the blackboard. Below the blackboard, there are 2 buckets that are initially empty. A move consists of erasing 2 numbers a, b, and replacing them with the numbers 1 and a plus b. Adding 1 stone to the first bucket and GCD of a, b stones in the second bucket. After a finite number of moves, there are s stones in the first bucket and 2 stones in the second bucket where s and t are positive integers. Find all possible values of the ratio t over s. What the hell?
Wow, that's like our reaction to every problem on this Olympiad.
Yes, APMO cancerous. Ban APMO
Man,
from
yeah.
future Olympiads. Let's try 1-1.
Hang on, I need to configure this first. Configure the stream, I mean. Image problem 5. This image is bulky. Okay, cool. This problem. I just finished reading it.
Sure, it's combi games, surely you could. Just find the invariant and then we're done, right? That's how you're supposed to do this question. Just find the invariant or the monovariant.
I mean, okay, so it's telling you to find all possible values. Should we try some small cases? N equals 3, I guess?
N equals doing that.
Right.
It's not organized. N equals 3. So start 1, 1, 1, and 1 and 0. Why is there 5 things to keep track of? Goes to 2, 1, 1, 1, 1. Okay, now there's 2 ways this can progress. This could be like 2, 2, 1. And this is like 2, 2. Or this could be like 3, 1, 1. And this is 2, 2. This goes to either. Let's go. First choose. This could be 4, 1, 1. And this could be 3 and 4. Or this could be 3, 2, 1. And this could be 3 and 3. And this can become 4, 1, 1, and it becomes 3, 3. Or this becomes 3, 2, 1, becomes 3, 3. In case you can just ignore the other case, right?
Um,
Okay, I'm thinking there's like every rational. Honestly, I'm just thinking it's every rational. I wouldn't be surprised if it is. It's just like,
Right,
yeah, it's
yeah.
every rational. But it has to be rational because fine, if it's irrational, then
GCAB. Oh wait, the buckets are ordered.
what?
The buckets are ordered, right? Which means that T has to be greater than S. So if your
Yeah,
conjecture is true, it's just all rational numbers greater than 1. But I feel like
greater
that.
than what you mean.
I feel like
Greater
it's
than what
not
you mean.
true. Yeah, yeah, greater than or equal to. But I feel like it's not true.
It's probably got an upper bound somewhere.
I feel like yeah, it's probably got some like, for example, I don't think you can get 11/10.
11/10.
Yeah.
What?
Oh no, wait, you could, right?
1,
Uh,
7, 1. I've got it. I've basically got it. If you 11/10, I know you can get from there.
hang on.
You still show every gap as possible.
Are we supposed to find the values of the ratio T over S for a? Oh right, right. In greater than to be a fixed
Then
integer. Yeah, it's in terms of n. Yeah, okay.
yeah, but you can definitely 11/10 because it's right. It's on this branch here.
Oh wait, what is it? Let me see.
This branch here. This branch gets you 11/10 if you just keep
Are you wait?
combining the
How
first.
are you wait? Oh, I see what you mean.
There's just me mapping every game. 5, 1, 1, and that would be 4.
Why does n have to be greater? Why cannot? Why can n not be 2?
Huh?
Why can n not be 2?
Because then there's only one game you can play.
Yeah, sure. That's still interesting.
Is it?
I mean,
It's always gonna be, you're just adding one to one. You're just adding one to both buckets.
are you? Right, right.
Just think about it. Yeah, you're just adding. It starts at 1, 1, and you get 2, 1, then you get 3, 1, then 4, 1, then 5, 1, then 6, 1, etc. And then the bucket's always going
Oh,
to be 1.
yes, yes. Oh, true, true. Okay, that means the all possible values of the ratio is just 1/1, right? Or like T over S equals 1. Okay, yeah. Hang on a minute. I'll be 3 minutes. Hi, I'm back.
I am back as well.
Oh, nice. Okay. uh,
Is it just me? Is this growing by Fibonacci? Never mind. It's 6. No. Wait, yeah, it is. Why is this growing by Fibonacci? The number of states.
wait a minute. Oh, interesting.
Is there echo now? This is so sad.
Wait, is the echo? Where? Is the echo? Brady's just watching it on 2 tabs.
Twice the views. Double the sound. I don't know.
Yeah.
Twice the
fun.
Four. Like, yay, we got a gap of 2, which means all the 2 gaps are possible now.
Nice.
Except, is 3 over 2 possible?
3 over 2.
Yeah.
Ah, right. True.
Is 3 over 2 possible? Is, let's think, what else? Is, 6 over 4, yeah, 8, is 8. I think you can't get the supreme value is 3 over 2.
Sorry?
I think the supreme value is 3 over 2.
Oh.
For
Oh, right. I see.
orange, T over F less than 3 over 2.
But like everything between 1 and 3 over 2 is possible.
Yeah.
Okay. That's an interesting conjecture. This is an interesting problem. So far.
So far. Wait. There's so many cases. I might have messed up somewhere though. Let me just double check.
Yeah, and there are like 5 things to keep track of.
Yeah.
Which is a little.
Maybe like a large thing. Can we add? Oh, you can add. This becomes. Oh wait, no, never mind. I got 3 over 2. It's in a later case in this thing.
Oh.
This one. There's 611, and this becomes 64. That's 3 over. Wait, never mind. That's 5-6.
Okay.
Figure this out.
Shouldn't it be? Oh no, yes, yeah. You're right. What if you do come down here. 4, 3, 1.
3.
And 5.
Oh, wait, that's what should be here. 4, 3, 1.
5.
And it's 5, 5. I already got it here, Tony.
Oh, right. Yep. And yeah, do another case, but do 4 and 3. Combine 4 and 3.
Okay.
Because now you get a huge number. You get a huge increase in T.
Do you?
Wait, it's greatest common denominator.
Yeah.
I'm so confused. Okay. Yeah, never mind.
It's going to be co-prime.
So you have like 5. Right. So the conjecture is still true, right? Or at least the conjecture hasn't been disproven yet.
Yeah, but I feel like we need more space. Um, how would you write this out well? I'm just trying to think. You want to make
You mean like representation? Like a good
yeah, just write
representation.
clean.
Here's an idea. Instead of writing t, write t minus s.
Okay, I'm fairly sure T minus S. I'm fairly sure you can just construct to be arbitrary. I know that, but the issue is you only figure out the minimum T and S for that. So what's the minimum number of steps required to get the distance between T and S to be 2 or distance to be 3, etc.
Yes. For n equals 3, it's quite easy to calculate that, I think. Yeah. I think for n equals 3, I've proven it.
3 over 2.
Yeah, yeah. It's basically like, so if you want t to increase more than s, then you need the GCT to be like not 1, right? And the most efficient way to do that is just to be like, get A and B to be equal to each other. Then the GCD is equal to A, which is also equal to B. But
Yeah.
yeah, and in that case, it takes exactly A plus B minus 2 turns to get there, and you increase T more than S by A minus 1, which is half of A plus B minus 2 on the next turn. So in total, it's taken you A plus B minus 1 turns to get T to be greater than S by A minus 1. So you can never get to 3 over 2. Don't know if you followed me there, but I can draw it out. To get an additional move to get to n minus to increase T. The last step. Okay. Wow. I'm using this thing called a sticky note.
Sticky notes on my Windows. I used to on my Windows notes computer.
No. I'm talking about like a sticky note in Google Jam board.
Oh.
So yeah, the the thing with n greater than 3 is that it doesn't necessarily take 2n minus 2 turns. So that thing is false now. Wait, Sharky, are you there?
Yes.
Okay.
Some sequence thing of my own.
Mm, 5, 10. Hang on, I think I just got 3/2.
Okay.
So have a look at this, right?
Slide 12. Yep.
Yes. Uh, so you can do like eventually it'll get to 4, 4, 1 with 6, 7. Is that true?
Yes. Yep.
Yeah. Now you do
And
the
then you
two
add
fours and you
4.
get like 7, 11. There we go.
Yep. Oh, that's greater than 3/2.
Yeah.
Yeah, I was doing something similar. I didn't have
And
love to that.
that means you can also get 3/2 because you can just do 8, 11, 8, 12. I mean, on the next one.
Okay. If it gets progressively harder to get past the halves, presumably, then new supremum, let's say it's like what, n-1 or something, or 2 in this case. So yeah, saying n-1 is the new supremum value. It's either 2 or n-1 as the supremum for all n. Yeah, I actually got 3/2.
Yeah, I got
Mm,
3/2. You just do 7 and
One.
11, and you add 1 to both, right?
Yeah.
Yeah. I'm just thinking, what happens if you just repeat that process that we just used to get 3/2?
Yeah. And then just repeat it to get like numbers. That's definitely bounded over. Like yeah.
I think this is the fastest way to increase your fraction.
Yeah. Well, at the very least, it seems like it. Well, I think it's exhaustive as a method. I think like because you're using my thing before for just adding ones and all that, you get like you can generate every single gap. Like if you have for a fixed d, you can generate q minus d over q.
Yes, yes. Yeah. So
Yep,
it
and
gets
then
like every
and you
yeah,
can
yeah,
just
yeah.
show that every single gap is possible now, and then that means every rational is constructed between those. You can just flex on us by saying 1, 2, 3, 4. I'll quickly solve them.
Lumao. Hang on. 16, 16, 1, 15, 30.
Are we both doing the
31.
same exact same construction for 3? Because I'm doing it on the slide 13.
Sorry, what are you doing?
I'm doing the same thing as you in slide 13. Just let me think.
Wait, I'm doing this. Oh, slide 13. Oh. I think we are doing the same thing.
Okay.
I calculated on this note here, on slide 12.
Notice.
Oh, hang on, that's wrong. I'll edit it. It's 58, I think. That's very close to being 2, actually.
Okay, can we exceed 2?
Yeah, I don't know. Let's try. 32, 32, 1. You add 31, so 62. 89. And then 64, 1, 1. Plus 32. Did I go wrong somewhere? Three, 4, 7. Eight plus 15. Oh, that's why. I did go wrong here. – Okay, I don't think you can ever get to 2.
What's that?
Sorry?
You say so. Asking why.
Right, yeah. However, I think you can get arbitrarily close to it.
So therefore, supreme thing.
So like the n equals 3 case is pretty easy to like do calculations in because there's only like your choices at each step are so limited.
Yeah. If in Ross's eyes we haven't solved their questions,
Lol.
this is true. Please, can you not demotivate us?
Okay, so with n equals 3, what you can get is this. S equals 2 to the n minus 1. T equals 2 to the n plus 1. Hang on. Minus n minus 1, I think. Seven. Oh wait, no, this is 6. Minus 2 maybe. Yeah.
To the binary for like n equals for like big N. I think it was.
Sorry?
I'm doing n equals 4 now. I think the binary thing's 4 powers of 2 saying binary.
Yeah. So I think we've proven that for n equals 2, you can get any rational number between 1 and 2, excluding 2.
Yeah.
Yes, okay.
Yes.
So now let's do n equals 4.
You can have a good slide that.
Slide 13? Right.
Yep.
Right. Oh, right, you're doing it. I see. Nice. So I think we're only interested in the fastest way they can increase because we only need the upper bound and everything else is just kind of doable, right? Surely.
Have I taken too many steps or something? I still haven't escaped too.
Wait.
Oops.
I think you made a
Yeah,
mistake somewhere.
okay, I've escaped too.
Oh, okay.
I think that still reinforces my idea that Knight probably is n-1. That's the supreme value.
Yeah. That seems plausible. And it works for n equals 2 too, right? Because it works for what is that
Well, no, n
variable?
equals 2, it's not the supremum, it's the exact value.
No, but it's the supremum of the set containing 1 is just 1.
Yeah, just remember that, yeah. N-1. Um,
Yeah. Okay, so
ST, that.
now
ST, S comma T, S dot T dot. But yeah, this should work. Just the binary thing. So, like, I think we can just extend this binary thing just in general to prove that the supreme we can never reach mi.
sorry, say that again.
I'm fairly sure we can extend the binary thing just to show that the maximum value is mi.
Right, yeah.
Sorry,
Okay. I mean, what is
what is it said?
what's the analogous formula for n equals 4?
Wait, no. What formula have you done? Oh, that thing, Nick. Well, I mean, look at 211 is 11, then 411. Then it's then I can't.
I'm gonna do another sticky note.
Surely you can recurse back just using the -1 case. Like you ignore the first one and just look at the the previous one, right?
Yeah, you could. Yeah.
Yeah, that probably gives you the values that you're looking for. I'm fairly sure that's just basic maths. You can do that fairly quickly. Now you just have to show it's elite. As always, less than -1. Be right back. Toilet break.
Okay. Hmm.
Back.
Cool. I just had a really interesting interpretation of this problem.
Cool.
So let's assume that you can only add two numbers when they're the same, right?
Yeah.
In that case, basically your array of numbers is it's like that, the 2048 game.
Yeah.
Yeah, so it's kind of like that, and the S tracks how many moves you've made, and T is like your score.
Sure. Guess that still works. But like, that's what our strategy. The thing is, you have to show it regardless of the strategy. You have to show that you get your thing.
Wait, what? No, you get to pick a strategy.
No, but you want to show that it's always bounded regardless. Like the thing you're saying, like I think we can easily show that our strategy like generates everything, right?
Does it? I'm pretty sure it doesn't. I mean, in 2048, the scoring is a little different.
No, but like think with this strategy that we're doing, right?
Yeah?
We generate like fairly large differences, and then just by combining two ones together, we can generate all the fractions with that difference. Yeah.
Wait, hang on.
So for example, look at my slide 13, right?
Yes.
This means that we can generate all numbers which are like 31 plus a over 15 plus a. Yeah.
Yes.
And so since we know we can generate like this as arbitrarily large, this difference is arbitrarily large as possible, just by like extending that sequence down. And this covers like this goes to like every single this should cover like every single fraction that's like
Wait,
got that difference.
hang on. Sorry, I'll be a moment. I'll be a moment. 怎么了？怎么了？
结束以后去装车柴火回来。
哦，OK。
你大概几点钟结束？6点吗
6点，可能6点半这样。嗯。
那太好长时间了。天黑了啊。
Sorry. Okay. Yeah. I'm back.
So like generates.
Yeah. No. I know. I think I know what you're trying to say. But like, um, yeah. What I'm saying is that oh, here's another interpretation, right? Like the algorithm that you use is you just take the leftmost two values that are the same and you combine them.
That's literally what the thing is.
That's what you're doing, right?
Yeah.
Yeah, okay. Right, and you just need to figure out what the score is.
We only have half an hour left. Should we go and type up the solutions?
So what for the other ones?
Yeah, we only have half an hour left.
Wait, what do you mean? Like we can write all the solutions after.
Oh wait, yeah. But regardless, we have to show regardless of how we play that the ratio should be less than n-1.
Yes,
Like
but
we've shown that we can, and that our thing probably generates every rational, right?
Yes.
But you have to show that the ratio can't exceed.
Yeah. Well, we kind of already know what the optimal strategy is, right? So we just have to show that that doesn't exceed.
How do you show that's optimal?
Um.
That's the thing. I'm thinking like, okay,
Right. I see.
you're saying it's an optimal strategy, but how do you know that's optimal? I mean, GCD is kind of weird for this, I guess, because you can't really bound with GCD.
Well, GCD, you can bound GCD.
Well, GCD is like less than the minimum of the two
Yeah,
numbers,
exactly,
right?
exactly.
Only one we know. Is that strong enough?
I think so.
I'm going to 14. Why would you? So you have. Okay, I have an idea. Add another bucket,
Okay.
but this one stores like just the minimum number, right? And then we show that it's like less than n-1s.
It stores the minimum number.
Okay, so like, when you do like your A1, A2, right, and you like combine them, and you get their GCD, and you put them
Yes.
in the T bucket,
Yeah.
get a U bucket,
Yeah.
and put in the minimum of A1 and A2 into that one,
Oh,
and keep
okay.
that.
Oh, right, right. Yeah, yeah, yeah. Okay, okay. Yeah,
Yeah,
yeah.
because with our strategy, that should be the optimal filling, right?
Yeah,
Because
yeah,
we
yeah.
always have
Okay.
the same thing adding up.
Yes, yes.
Yeah. So add another bucket.
Lol. Yeah.
I don't know. Let's try that. How does just model that first? Ones that we have, cases we rebash.
So yeah, well, in the cases we've already done,
Yeah.
it's trivial because our strategy was to only combine them when they're equal.
Yeah. Except for when you couldn't because there wasn't enough space, in which case you just added,
Right. Yes.
right?
Exactly. Yeah.
And when you add, then the U bucket actually becomes bigger than the T bucket.
Oh. Wait.
But like, if you can show that the U bucket is bounded, if U over S is less than -1, if we show that, which would be easier, I think, then we're done because T is less than or equal to U.
Right. Yes. Exactly.
So I'm just going to model this real quick. 1, so it becomes 5, then becomes 7, then becomes 10. And then this becomes 14. Then this becomes 3, 4, 5, 6, 7,
21.
21. Yep. So this would be 35. Wow, is these like pentagonal numbers or something? Then this becomes
Wait. Why is that 35?
because 21 plus 14.
21 plus. Wait. Where did you get
Oh, yeah.
14?
Sorry, why did you maximum? I was doing maximum. All right, so that should be add 1, 2, 3. Yeah, so that should wait 1, 1, 1, so 7. Yeah, and that's 11. Yeah, so in this case it should be equal, but otherwise it would be greater than equal to.
Well, yeah. So the only case when the U bucket becomes greater than the T bucket is when you run out of space in your array.
Yeah, wait, no, not it's because then our strategy was to just add, right?
Yes.
In our algorithm, this is the optimal.
Oh, right, right, right. Oh, yeah, yeah, yeah. Okay, okay, yes.
So yeah, this works on the optimal algorithm idea, right? But like actually like quantifying it, why is it optimal?
Yeah.
Like, our algorithm basically figures out how to add the minimum, the greatest GCD that we can find in this set. Well, if you have 4-2-1, then it's easier to go 4-3-1 than 4-4-1. Then you just go 6-1-1.
Right, yeah.
Okay. So now we have a bucket, and we want to show that bucket instead is. So let's say U plus equal to min. Wait, why did you plus equal? I can't do plus equal when writing maths. This is so sad. I do plus minus. I'm not used to U plus equal. A1, A2. Okay. RTP U on S less than n-1.
Okay, I'm just going to quickly check that if the array is infinite, then you can get unbounded by this strategy.
That makes sense. Because you can keep just generating a large power of 2, right?
Yes, but like the question is always like, why can't you for smaller when your array is finite, right?
Well, because you run out of space, so you can't keep
Yeah.
doubling.
So I'm gonna check that if you have an
okay,
infinite
cool.
array. Yeah.
Okay.
So 12. 14. 4.
I think UNS is like some average value. I'm just trying to figure out what it represents. Because then if you can figure out what it represents, then we can say that, oh, average is like less than n minus 1 because it's an average or whatever.
Right. Yeah.
Because division by S is like kind of like an average because S is just the number of turns you've had.
Right. Oh yeah, that's true. Yeah.
Yeah, so U over S is like your average kind of thing. I'm just trying to figure out how that would help. What's an interpretation of this question such that U would denote like maybe, I don't know, like I'm not sure what it would represent, but like some movement to the right, to the left or something like.
Wait. Sorry. Hang on. I'll be back. Wait. Hello. Wait.
Ooh, that's an interesting idea.
Okay. Sorry. I'm back.
Okay, I had a really nice idea.
Yeah. What?
Okay, so consider like you have, suppose like you had like another bunch of stones like that represent each value, right?
Yes.
Okay, so like you start with one stone, one stone, one stone.
Yeah.
then with the operation, you basically combine two piles, right?
Yeah.
So say you just shift one pile to the left,
Right.
basically, and then you add a new stone there at
Okay.
the place where the old pile was.
Yes.
Well, I mean, then basically U over S is like basically is the average of the number of moves each of your stones have done, right?
Oh, right. Yeah.
Yeah. But since each move only goes strictly to the left, you can only have at most n minus one moves for each of them.
Wow. Genius.
I think, but like that's less than or equal to. It doesn't show it's equal to. There's still equality there, but I think equality just doesn't work probably. Like in finite moves. Because yeah, I think that's right. Yeah.
Yeah.
Because yeah, basically moving stones only to the left in our thing. Because we're assuming it's ordered from left to right, descending order. I think that works.
It doesn't even have to be like left to right. It's just you just like literally keep track of how many times each stone has moved.
Yeah, but I think you get the n minus one because like you have to the left to right thing is just because there's n columns right in
Oh.
which so the n minus one comes from n minus one shifts to the left.
Oh, I see what you mean. Yeah, yeah, yeah. Okay.
But since it's starting, you already have some at the left. I don't think you can get equality.
Right. Yeah, yeah.
Yeah, so therefore it's less than. I think that works. And then combined with the fact that like t is less than or u, and you get t over s is less than minus one.
Right. Yeah.
Like we start with like this, and then this becomes and this would be like 0, 0, 0, 0, 1, 0, 0. This comes and this comes combined 1, 1, 2. Yeah, so something like this basically. And this would be like the sum of these values is your u value, and your you've done 3 turns, so this is just the average. So yeah, that works.
Wait, wait, wait.
Look in frame 14.
Yeah, I am. I am.
Yeah. You see what I'm doing, right?
Uh. Right. Yes.
Yeah. So I'm just doing basically the binary our algorithm with this idea of counting.
But how do we show that it's optimal?
Huh? No. The point is any sequence works like this. Every sequence will just that u over s value is your average of how many times each stone has moved. Does that make sense?
Okay. Yeah.
Like I can do it for any. I can even do something that's completely not in our algorithm. So say I added the first 2 columns here, right?
Okay. Yes.
1, 1, 1, 2, 2.
Yes.
And yeah, and then 0, 0. Okay.
You don't. Yeah.
Yeah. But if you add up the u values here, if you add up these values, these scores, right?
Yes.
And that I will tell you right now, that is the u value. That should be u value, and 7 over 4. No, sorry, not 3, 4, 5. 7 over 5 is your value for u over s.
Right.
In this case, in this thing, and this is always less than n minus 1 because of the it takes n-1 shifts to get from, well, it's at least at most n-1, since it takes n-1 shifts to get from the right-hand pile to the left-hand pile, right? But it's strictly
Right.
less than -1 because you already have some things in the n-1 in the other piles.
Yeah, okay.
And therefore U over S, which is your average, has to be less than n-1.
Okay, wait, let me think about this.
Oh dear, we're having
Wait,
an error with the string.
How do you... Sorry, what? What's happening? Oh. Wait, what? I don't know. I can still see the stream. Oh, was it? Is it better now?
Just check if it's better now.
Wait, where are you seeing those warnings? Oh, is that from the...
Stream us.
I think it should be better now. My network looks consistent. I'm looking at my network rates.
Okay, anyways, back to this. So, wait, so Tony, do you get what I'm saying with the...
Right, yes. Wait, why is U the sum of the the sum of all the...
Because, wait, no, so U is your counter, right? U is another bucket, remember?
Yeah. Oh, and
Yeah,
oh, right.
U is a bucket which
Oh,
adds
is it because
minimums.
doesn't this only work if the piles are always ordered largest to smallest?
Well, yes, we can warlock that, can't we?
Sorry?
Because we can warlock that, can't we? We can arrange the piles in any order we want.
Yes.
Because the order of the piles does not affect the question. So we can warlock it ordered, and then we can warlock that adding pile. When we do the operation, what we're doing is we're just getting the small pile, removing it from there, adding it to the larger pile, and then putting a new stone at the small pile.
Wait, okay, so wait. What about this? So we add
So just wait.
we like add stones to the left pile until it becomes like 5 stones, let's say.
Yeah.
And then we add stones to the middle pile so that it becomes 6 stones.
What? How are you doing that in one operation?
No, not in one operation, in 5 more operations.
Okay. But then we can just arrange the piles. Like, the point is...
Do you mean rearrange the piles?
Rearrange the piles.
No, but then that means that some of the stones may have moved 3 times.
Oh, wait. Wait, surely the order doesn't matter, though. We might have to show that it might be... Can we even do that, though?
Do what?
Okay, if we... Is it possible to get the middle pile to exceed? This one I'm thinking. Wait, no, we can. Sorry,
yeah,
my
of
bad.
course. Yeah.
Okay, so don't reorder. But like the point is, every time you do an operation, the stones move to the left. Sorry, yeah, that's it. Sorry, my bad. Every time we do an operation,
yes.
right?
But that means that U doesn't count. the thing that we want it to count, right? We have to maybe like modify it.
Maybe, yeah. But it's whatever. Yeah, but that still means is U is at least the minimum though. So it doesn't, because I was just adding minimum, but if U is at least a minimum, right?
U is yes, it is.
And since it's still going to be less than n-1 because of the fact that there's stones that are at the end piles already.
No, but if it's at least a minimum, then it could be like anything.
Well, yeah, but the thing is, it's bounded.
Wait.
By n-1. Because the average, U over S is the average. And the average cannot be more than n-1 moves.
Right.
U over S is the average number of moves each stone has done. And each stone cannot move more than n-1 times.
Okay, yes.
Yeah. And that means that U over S is less than or equal to n-1. Because the average, because it can't exceed n-1, so therefore the average itself has to be less than or equal to n-1. With equality if they're all n-1, which is not true because some stones are not going to move n-1 times. Like the one at the very start, the one that's in the top pile at the very start, will not move at all.
Yes. Yeah, I know.
So therefore, the average has to be less than n-1.
Okay.
Like yeah, my U definition might be a bit dodgy, but yeah, U is like the right pile being added to the left pile. So we can reword this question to be a movement on stones, moving stones around.
Right, okay, yes, I think this works, yeah. So, okay, so wait. So what we've shown is that, yeah, okay. So, if for some n, we can get all the numbers, we can get all the rationals between 1 and n-1, right? Okay, I'm going to just like do some empirical checks.
I'm just want to double check that we can get every rational. But I'm fairly sure my argument works for the U over S is less than -1. Therefore, T over S is less than -.
Right. For the inequality part, it's slightly different, but it's still true. So, like, the proof of the inequality part has to be tweaked, but it's still true, yeah.
The only thing is you have to tweak is the definition of...
Well, you have to note that some stones are always moved one time, because the zero stones don't count.
I mean, yeah, they do.
No, because the zero stones aren't stones that are added, because S only counts the stones that are added, right?
No, S is the total number of moves. U is the...
S is the total number of moves, but it's also the number of stones that are added, right? So if you want to average, you have to average over the number of stones that that weren't added. Like, wait, sorry. That were added, yeah.
0 stones here, there's 1 stone here, there's 2 stones here. 3 stones here,
Yes.
4
So
non-zero stones here, 5 non-zero stones here, and that's S1, S is 0, S1, S2, S3, S4, S5. Yeah.
yes. So that means since there are always stones that have moved once, that's less than n minus 1 for n is greater than or equal to 3.
Yeah. I mean, basically there exists S stones always with the non-zero number of times they've moved. Okay, we can just say that instead. That's the definition of S. It's the number of stones that have moved at least once.
Yes, exactly. Yeah.
Yeah.
Wait, but how do we prove that you can always get at least? You can always get like arbitrarily close to n minus 1.
What the power of 2 thing is.
You mean just using our strategy?
Yeah, use our strategy to show that yes, we can get as close
Right.
to.
So that's just like computational. Is that what you're saying?
Yeah.
Okay,
That's
sure.
computation.
Yeah, I guess. Yeah.
Now
Okay.
we just have the rational thing, which also follows from differences that we can generate. Because you can generate as long as you get arbitrarily close to n minus 1, we can also get arbitrarily large differences, which means we should be able to cover every single rational in between.
Right.
We only have 2 minutes left.
Lol. I mean, I think we've solved it, right?
Yeah, we've solved it.
Nice. Okay.
Oh.
Well, is it time to write up solutions or something?
Yes, that was tough.
Lol, yeah. That was a nice question. Nice problem.
Let's just hope we didn't fake solve Q3.
Oh, yeah.
Alright, I'll line up Q1.
Sorry?
Q1 up.
Okay.
Yep. 2 minutes, right up.
Yeah.
Just watch us. God damn it, I'll try and copy paste them.
All right.
Wait, only one person solved this question? Oh, probably because
Question-
they need.
Yeah. Only one person solved question 5.
Probably because there's not enough time.
Yeah.
Because I think Q3 would be pretty harsh.
I don't know what's up with APMO, but like problem 4 is always easy. Like a lot easier than
3 and 5.
Yeah, I swear, like every time I've taken the
Yeah, 5 was
APMO.
easier. Last year 5 was easier.
Right, oh yeah, true, because
7,
question
4, 0,
4 was
7.
yeah. But like in the years I've taken it, because problem 4 is just a troll. Alright, I guess I'll write up problem 2.
Okay, so
Um
Okay, but you have to realize you were also fairly busy throughout the entire thing. So we get at least half.
hang on. Why is this
You
not
on the
showing?
overlay?
Yes, but I'm fixing the stream. Here we go.
Rip not. Oh, so APO. One up. Who's this? Oh, right. Can I come some more content providing that up in Tom?
Sure, okay.
Oh, I only said ceiling and 1 on epsilon because that's like the smallest integer that's greater than 1 on epsilon.
Are you talking to me?
In the question 2, that's why ceiling at 1 on epsilon. I think I wrote that down, or did you put that in there? I can't remember.
You wrote ceiling of 1 over epsilon, right?
Yeah, and that was because you wanted it to be, yeah. Yeah, and that's like the solution we had for like 1, 1 or whatever. Epsilon equals 1.
怎么了？怎么了？好的，等一下啊，我弄一下。Rip, I have to go eat dinner. Should I end the stream now or should I keep it going?
And
Sorry?
now I reckon. I don't think people are focused on watching this type.
No, but like if we keep going, like at least we will record it. But like, there's nothing to record either, right?
of thing. Like if there's any latex that people that
Yeah, it's
we
not
type
very
out.
interesting. I'll just end it now. All right, well, yeah. If you guys watched this far, I guess this is the end.
Hit the like and subscribe button, ding that notification,
Yeah,
subscribe to Patreon.
you gotta AMGM the like button and induction the subscribe button. Sorry, yeah, I don't know. Okay.
Whatever.
Yeah, how do I end this?
No idea. Ask Brainy.
Yeah. Hi, Brainy. How do we end the stream? Oh, it should be stop streaming on OBS, right? Yeah. Okay. Yeah. Cool. We'll look in the description for like the Jamboard and Overleaf, which we'll post when we're finished with them. Cool. Okay. See ya.